Alright, so I recently found more issues with our conception of how exponents work. Right? So generally what you'll see is things like 2 to the third, right? Will be the way it'll be said is the really common way that basically everyone said up until a few years ago was this is or like a to the b. Whoops, that's not the right character. There we go. Is the base a multiplied by itself b times, right? So that would make this 2 multiply it by itself once, twice, 3 times. Oh my god, look at that. Okay, so that's an old way of saying it, which is still around. I see it regularly still. Okay, another way to say it is b copies of a multiplied together, which at least we're doing better now. So now I have 3 of these, and I just drop multiplications between them. Okay, that's at least the right numerical value. Okay, but there's something else missing here. What if we hit on this guy? What is this? What is this? Well, it's 1. We all know it's 1, but why? How? If a to the b is b copies of a multiplied together, how is a to the 0 equal to 1? Right? That should be, okay, a to the 0. Let's try this. Let's follow this rule that's outlined up here. And there's slightly different wordings of it, but they all kind of boil down to this. B copies of A multiplied together, I just don't have anything at all. That's numerically wrong. It should be 1. So what this really, it needs to start with 1. Multiplied by A, B times. Now, we start with 1, and we multiply it by 2 0 times, so we just don't do anything. Okay, here we start with 1, and we multiply by 2 3 times. There's 1, 2, 3. Look at that. How about a negative exponent? So now you start with 1, and you multiply it by 2 negative 3 times. That means the negative of multiplication is division, right? So divide by 2, divide by 2, divide by 2. There you go. Okay? Now, there is a further problem. There is a further problem here. Generally, in order to get imaginary numbers, complex numbers, you need to raise a number to a complex power if we're using exponents to get there. So, like, well, we'll use a nice famous simple one, right? E to the I pi is negative 1. But if we just cut this in half, there you go. There you go. That's an imaginary number right there. We just raised a real number, e, to an imaginary power, and we got an imaginary out of it. But notice something that just happened there. I'm going to stick with pi for the moment, even though I might have to switch out in a second. But for the moment, I'm going to stick with pi. So pi gave us -1. Let's write them both down. Pi on 2 gave us I. This division on 2, you might notice that I is the square root of -1. So we're able to factor this 1/2 out of here and put it onto a real number and still get an imaginary result out. The real number has to be either positive or -1, but we're able to get imaginaries by using real exponents on certain real numbers. Okay. Now, if we take this a little bit further, what if we just look at something like the square root of 1? Right? We're familiar with 1 as a possible solution, right? Probably also familiar with -1 as a possible solution. Okay, because if we follow our rule up here, 1, yeah, let's just reverse it. So -1 squared gives us 1 times -1 times -1, which is 1. So -1 is a valid square root of 1. And if we just kill the negatives, that also works. So both 1 and -1 work for that. Now, what about something like this? So this root, this is a square root. It's less than 1, that power that we're putting on it. What if we introduce a power greater than 1? Well, conventionally, we're told now it has to just be this, right? Because the way this has to work is if you're taking 1 and you're raising it to a power larger than 1, then it's just 1 times itself over and over and over and over, right? Problem is, what happens if we try doing this? So let's try -1 to the, and then I'm going to invert this fraction. Okay, so first off, we can do this 2 different ways. One, well, we're going to do this. We could take the cube root of -1 and square that. So this could be -1 to the 1/3 squared, or it could be -1 squared and then the cube root of that. We could think of this either way. Okay, so let's say, oops, let's take this one first, because I wrote it first. So the cube root of -1 has to be -1. Right, so what we're going to do, right, -1 times -1 times -1 with a 1 out there. Alright, so this is -1 cubed. Okay, so this whole part here is just 1, 1, times negative 1. So we get out a negative 1. So the cube root of negative 1 squared is the same as negative 1 squared. We know how to do that. It's just this, which is 1. So negative 1 to the 3 halves is also validly negative 1. And if we reverse it, here this one is easier to see in your head, so I'm just not even going to write this out. If you square negative 1, that's already 1, and then we take a cube root of that, well, to get the positive 1, it has to just be 1. They all have to be positive, right? So just flip all these signs to positive, and there you go. But now, wait, what if we did this? Let's make it, well, here, let me show you something. So it doesn't matter what this odd number is, right? It could be 7. It's still the same thing, right? Okay. It turns out, because of the way this is working, because there's an actual, just any integer multiplier in there, you can just drop anything in there, right? For any integer n, or well, let's see, in this case, that's not quite true. I'm not gonna modify that so that is true right now, but yeah. You can get that on there if I'm not using pi. That's why I was gonna change it from pi later on. Yeah. Anyway, yeah, you can get a multiplier on there, right? It's periodic, right? E to the I pi is negative 1. E to the 3i pi is negative 1. E to the 5i pi. Notice those are these odd guys right here, and pi is half of the distance around the circle. So that's what's happening here. If I did e to the 2i pi, that would be positive 1, right? And if then I can, yeah, I can just do any odd number in the numerator, and then I can do any multiple of the odd number, which will give us the odds and the evens. So then we, because the system is harmonic, or yeah, it repeats. It's periodic. There will be half of these things will multiply this by an odd number, and the modulo will be odd over 2, or 1 over 2. And half of them will multiply it by an even number, and the modulo will be just 1. So we'll get the full circle instead of the half circle. So we'll come out on either 1 or negative 1. So we validly get an integer, 1, a real integer, 1, raised to a power greater than 1, which yields negatives as its solution. But it's nicer than this, because what if we did something like this? So if we look at 1/4, 1 to the 1/4, it turns out we get this. And guess what? That works for all odd numbers over 4 for the same basic reason. Right? It doesn't matter what that number is. If it's odd and it's over 4, 1 raised to that power gives you these guys. Right? 1/4, 3/4, 5/4, 7/4, 9/4. It doesn't matter. As long as it's odd over 4, you get those. So you get a real number raised to a real power that gives you imaginaries. And it doesn't have to be roots of 1. Like actual powers of 1, right? So roots are when the exponent is between 0 and 1, and powers are when the exponent is larger than 1. So in this sense of these vocabulary terms, we're using a power, not a root. And we're getting imaginary numbers with a real power and a real base. This is not at all even accounted for by the way I'm saying things here, right? So this is already massively more correct than the ways that it's normally said, but it still doesn't account for this. And I've been searching the internet for like a week or so, looking for anyone talking about this, and I can't find it. So I seriously doubt that I'm the first person to recognize this by any means whatsoever. But it's certainly not easy to come upon. Nobody's talking about it. I don't see it in textbooks. I don't see it anywhere that this is happening. But another way you could think of this is, right, we're taking the 4th root of 1 and then we're raising it to some odd power. And it turns out when you do that, all of these solutions work. So that method that I showed with showing that -1 can be like the 5th half power, the 5 halves power of 1. You use that same process, right? We take the 4th root of 1. It's going to be this. It's going to be this. Technically, there's more details to this actually. Because there's a distinction made in this system between 1 and +1. Right? So we have, in general, e to the, and here's where it can be, where for any integer n, we get this. Call that tau if you wanted to. Instead of 2 pi, you could call this tau. I don't really give a shit. Okay, this one is 1. So if your n is 0, we get e to the, it's just 0. Right? But you can put all that on there too. And now, by our definition of how exponents work, that's just 1. But we can do other things. So if we get 1, then we just get our identity, Euler's identity. There we go. E times, what am I doing? I pi? Or, no, not quite. I got excited. Never mind. It's sort of our Euler's. It's, yeah. It's not quite Euler's identity. That one? Yeah, I'm not going to go through all of these, but you might notice that the ones where this works for are these ones. Not here. Not this one. This one's different. So 1 to the 11/4 just equals 1. So this is actually different. This is a positive 1. It is distinguished. So this is yeah, sort of not true, because if n is 0, then it does actually behave differently. And that is also something which we don't have covered in our classical sense of how anything works. But it is necessarily true, because while this system is periodic here and allows us to get at this one is aperiodic, completely independent of everything else, and it does not play along with that system. It is distinct. There's another nice little thing, which is any power of 1, positive or this guy, just the bare dimensionless unit. One of the solutions to any exponent will always be, well, if it's 1, it'll be 1. If it's positive 1, it'll be positive 1. Right? One of the solutions to that will always be this guy. This guy. This guy? Yeah. So 1 raised to any power, 1 is always an option. But, yeah. So let's see. I'll write this in here somewhere. So while this is true up here, the bare dimensionless 1, multiplicative identity, it's always just 1 for any real k. And the other one, positive 1 to the k, always has positive 1 as a solution for any real k. I've never seen this mentioned, ever, but it's definitely true.